Today we're going to be talking about conditional probability in models. This is some heavy stuff, so you might want to check it out a couple times, and I highly encourage questions. So the first thing we're going to talk about is conditional probability, and that is how we formulate probability of events when we have some information about what's going on. So one way of putting it is we know some of the answer, and that changes what our ultimate opinion about the probability of the next thing happening is. So a classic game show with a host named Monty Hall had a game where there were 3 doors. One of them had a prize behind it, and the other 2 were empty. And so the game proceeded. First, the contestant chose a door, and then the host knows which one has a prize behind it. So the host opens one of the doors that doesn't have a prize behind it. And then they ask the contestant, should you switch? Would you like to switch, or would you like to stay with your initial choice? And the question is, from a probability perspective, what is the decision that gives you the best possible outcome? In other words, we have a question of what is the probability of winning given either the condition that you switch or the condition that you stay. So that's conditional probability. So you can map it out. So here's the 3 doors, and you might have chosen the empty one, or an empty one, or the one with the prize behind it. In these 2 cases where you chose an empty one, if you switch, because that leads you to the one that wins, right? Because at the empty one, if you stay, you're on an empty one. You switch, you win, because the other door that's been opened is empty. And then in this last case, if you picked the winning one in the first place, then if you switch, you win. You lose. And if you stay, you win. So whether you win or not depends on whether you switch or stay. And so let's talk about that. So there were 2 different ways to win. If you switched, you won 2 times out of 3. And if you stayed, you won 1 time out of 3. And go back and show that, right? So you don't know which of these states you're in. So if you switch, that's the thing, right? You don't know where you are in these. So if you switch, 2/3 of the time you win, 1/3 of the time you lose. If you stay, 2/3 of the time you lose, 1/3 of the time you win. So we say that the probability of winning given that you switched is 2/3, and the probability of winning given that you stay is 1/3. Interesting. So this is important notation, right? So the capital P for probability, and then the event we're talking about comes before this vertical bar. And then after the vertical bar is the extra information we now have. And then again, these probabilities are only always between 0 and 1. So here's another way to visualize it. If you have, so you 2/3 of the time your initial choice is empty, 1/3 of the time your initial choice is prize, but you don't know this. All you know here is what happens if you stay. So 2/3 of the time if you stay, you lose. 1/3 of the time you stay, you win. 2/3 of the time if you switch, you win. 1/3 of the time you switch, you lose. And that works because the probability that you win a prize given that you're staying is the same as the probability that your initial choice was the prize. But that's only 1 in 3. And the probability that you win the prize if you switch is the probability that your initial choice was one of the empty ones, which is 2/3. So sometimes you can find a conditional probability in terms of a non-initial probability, a non-conditional one. So lots of different ways to express conditional probabilities. So I'm going to give you some more examples with dice that hopefully make sense. So we have, here's a table here. So this is what happens when you roll the first die. This is the result of the second die, and then the combination here goes from 12 to 2. 7's along here. So we can visualize some of the probabilities. So for example, the probability of rolling a 7 or greater There's 15 different ways out of 36, so that's 5/12 or 0.42. So there's no conditions here. This is just the probability of rolling 7 or greater on 2 dice. But we could say, what's the conditional probability of rolling greater than 7 when the first die is 4? In that case, there's only 6 different outcomes, 5, 6, 7, 8, 9, or 10, and 3 of them are greater than 7, excuse me. So the probability of rolling a 7, given that the first die is 4, is 1/2. So this extra information changes our probability. Here's another example. So if we want to know what the probability that rolling a 4 on the second die is, there are 6 ways to do it out of 36, so there's a 1 in 6 chance, 0.17. And if we roll a 4 on the first die, there are 6 different ways for that to happen, and only one of those is a 4 on the second die. So the probability of rolling a 4 on the second die, if the first die shows 4, is also 1/6, just like it was for the whole thing overall. So in this case, the probability that the first die was 4 doesn't give us any information about what the second die is going to be. And so because the probability didn't change, then we say that there was no extra information here. And we say that the two outcomes are independent. So if the probability of x, given that we now know y, is the same as the probability of x whether we knew y or not, then they're independent. So that's an important thing for probability. If you compute the conditional probability and it's the same as the original probability, then those two events are independent. And that's pretty important for stats. So that's conditional probability. I hope that made a little bit of sense, and I'm going to move on to the next topic.